asked for before we finish. The next talk will be by Nisheeth on many interesting topics mixed together. So I'll let him take over.
Thanks, Chandra, for this talk. So as you can see, that this title is really quite a mouthful, so I'm not going to try to explain to you, but hopefully by the end of the talk, at least you understand the title and all the terms. So, but let's start with the problem, which is perhaps easy to appreciate and has also applications. So imagine that you're given a graph on n vertices, and for every edge in this graph, you're given a vector, v sub e, which you can think of as a matrix, capital V, which is an n-1 cross M matrix. So these vectors live in n-1 dimension. That's really the dimension related to the graph. So, and your goal is to find a spanning tree in this graph, which maximizes a following volume-like quantity. So if I look at, for every edge, this vector VE in the spanning tree and look at the volume of the simplex formed by these vectors, I would like to find a spanning tree with maximum such volume. So in matrix notation, we can write this quantity, the volume, as the determinant of V sub t transpose V sub t, where V sub t is the columns of the matrix V corresponding to the edges in the tree. Okay, so this is a simple to state problem. It turns out that it can capture many optimization problems by playing around with different vectors. You can get pretty much your favorite problem out of it, what we would like to do is to find approximation algorithms for this problem. So this is more of a mathematical motivation. A more machine learning motivation comes from this data summarization problem, where you're given a bunch of vectors, one corresponding to each document. So think of these vectors as feature vectors for a document. And there is a sense of diversity of these vectors. So which is the measure is exactly the same as what I described in the previous slide, that if you give me a subset of this set of documents, we can measure its diversity depending upon the volume of the simplex formed by these vectors. And this measure has been used quite a lot in machine learning, and there's a survey by Kulesa and Taskar on this. These kind of objects are also called determinantal point processes. I'm not going to go too much into that. So, but what is the real problem? The problem is that often we are interested in not only finding a subset, any subset, but a subset which satisfies certain additional properties. And these properties typically correspond to things like fairness constraints or resource constraints or budget constraints that you impose on the subset of documents that you're trying to select. And combinatorially, we can think of being specified a subset B of this entire subsets, the set of all subsets of 1 to m. And the optimization problem that we want to look at is maximize the determinant with respect to sets which lie in this combinatorial family. So there is a discrete part, which is the combinatorial family, and then there is a continuous part, which are these vectors, which have some geometry associated to them. So here's an example for when B is a partition matroid, we are given subsets of the ground set M, P1 to PT. They're all disjoint. We're also, in addition, given some positive numbers, B1 to BT. And what we would like is that the set S that we pick has the right intersection. In this case, S intersected with PJ is BJ for every part. And you can imagine that your set of images is divided into two parts, male and female, and you would like an equal representation from both males and females, while at the same time trying to maximize the geometric diversity of these images. Okay, so, and the example that I talked about in the previous slide, spanning trees correspond to B being roughly a regular matroid, And in this case, the specification of this family is given by the graph, whereas in this case, the specification of the family B is given by these sets and these numbers. Okay, so it's not always clear how we would specify the family B. In different contexts, the specification could be different. So let's just focus on these two. So think of this as a partition matroid and think of this as a regular matroid. And these are the two combinatorial objects that we are going to focus on. And we will address this question about finding efficient approximate optimization algorithms for these classes of matroids. So there is a large body of prior work for this problem. So it started with Khachian's work on this family B, which corresponds to picking a single cardinality constraint. So this set B is now all subsets of the ground set, which are size exactly n. And Khachian gave an n to the n approximation algorithm for this problem. And this was improved by work of De Summa, Eisenbrand, Faenza, and Moldenhauer, and more recently by Nikolov. And the approximation is something like e to the n. And in case you wonder if you can approximate it better, the answer is not quite. So maybe you can improve this constant e to something better than e, but the form of the result will not change drastically. So it's hard to approximate better than c to the n for some c, which is positive. A more recent and a different line of attack on this problem is this following set of work, starting with the work of Nikolov and Singh, who gave an algorithm which estimates the value of this optimization problem. Okay, and in fact, Nikolov and Singh generalized the result of Nikolov for a single part to multiple parts. However, their algorithm could not output a set S, could just output the value. And these results were then subsequently generalized to various other matroids and in a more general setting. So I talked about this in a couple of weeks ago, so I'm not going to say too much about this work. The issue with this set of work is, so the first thing is that these works somehow seem to rely on this theory of real stable polynomials, which is delicate and also not clear when it holds and when it doesn't. All these relaxations, all these algorithms write down a certain convex programming relaxation for the problem, and the computability of these convex programming relaxations is actually quite non-trivial. It's not obvious how to solve these convex programs, and in fact, it turns out to be a kind of a very nuanced question. But most importantly, these are all estimation algorithms. They give us no idea as to what the set S would look like. And this is the problem that we want to address. Can we find approximation algorithms for this constrained subdeterminant maximization problem, which are close to in their approximation ratio for so clearly for this simple setting of one part, these results are, there exist such results, but when we go to more general matroids, we cannot find such results. Okay, so this is our main contribution. So the first result is about regular matroids, where we give a randomized approximation algorithm. So this algorithm works with high probability and outputs a set S such that its value is within a 2 to the minus m factor of the optimal. So I'm not stating the result in full generality, but roughly this is what the result says. So this is the kind of factors that we were seeing in the previous slide. And the distinction from previous work is that we can also output a set S. So this is the result for regular matroids. There's a similar result for partition matroids, where the quality of approximation is this formula. It depends upon the size of the parts and the number of elements that you can pick from each part. This is a bit mouthful. I think the simplest case is when each part has a constant size, let's say 100, and in that case, this approximation can be seen to be e to the order r, where r is the rank of this matroid. So these are our two main results. approximation algorithms for this constrained subdeterminant maximization problem in fairly general settings. And while we do not match the approximation ratios in all cases, as mentioned in the previous slide, certainly in various interesting cases, the approximation ratio of our results is also tight. Okay, so I guess the main technical tool which we use to prove this is what is called an anti-concentration inequality. Well, I guess we had a talk just before on concentration inequalities. Anti-concentration inequalities say kind of the opposite, that you have a measure space and you have some function acting on this measure space. It's supposed to be anti-concentrating if it doesn't clump the mass in any region of this, if its range. Okay, so you have some domain and you have some function which acts on it. So it could, in principle, map this whole thing to a single point in its range. And that would be quite bad for us. So what we would like to understand is, when do functions have this property that they are kind of well spread, so they don't concentrate mass at any small subset of its range. So such theorems are called anti-concentration theorems. Their study has been rather recent in mathematics, and it's not at all anywhere close to the kind of work that we know, the kind of results we know about concentration results. Okay, so before I state our theorem, I need a definition, and the definition is the following. So it's a notion of smoothness of a function, of a univariate function. So I have a function from 0, 1 to non-negative r's, and we say that it is smooth if for every constant in the interval 0, 1, the probability that the value of g is at least c times the maximum value is at least 1 minus 2c. Okay? Well, maybe the other way to think about it is the converse, that the probability that g of x is less than c times g max is less than 2c. So almost everywhere in this interval, the function takes value which is close to the maximum value. Okay? Well, by almost everywhere, I mean this with large probability. So how good an approximation you want? Yeah. Yeah, under the uniform distribution. That's right. Yeah, so we have a uniform distribution over 0, 1. And if, okay, so for a multivariate function is said to be smooth if this condition holds for every restriction of f along a line. Okay, so if you take any line in this m-dimensional space and you restrict the polynomial or the function onto this line, then it has this property.
So not just coordinate directions.
No, not just coordinate directions. Okay, so and the theorem says that if you have a function which is smooth in this sense, then at a random point, its value is a good approximation to the optimal value.
What is op?
Sorry?
What is optimal value?
So optimum is the maximum of f of x in this domain 0, 1, m. Yeah. So sorry, I forgot to put that. Yeah, so optimum is the maximum of f of x in this entire range, and what we are saying is that if I sample a random point, then it gives me a good estimate or a reasonably good estimate of the optimum with high probability. So there are two constants here, two numbers here. One is this approximation ratio and one is this probability. And in fact, the result is much more general. It applies to product of simplices, and also these numbers can be traded off in a variety of ways. So I just state a very special case which we are going to use in the results. Okay, so this is our anti-concentration inequality, And let me mention also a related result by Carberry and Wright, which proves something similar in the Gaussian world. But you can use this result to derive a result such as this, where instead of e to the minus 4m, you get something like m to the minus m. Okay, so you can use some existing results from mathematics to get slightly weaker bound than our results. Okay, so let me with this tool, let me just tell you now what the algorithmic approach is. So the proof strategy is the following. So remember that this is the problem that we want to solve, and the first step is to write down a function f of x from the domain 0, 1 to the m, so that the maximum of this function is very close or even equal to the optimal value that you're interested in. So this is an NP-hard quantity to compute, and so we can perhaps think of encoding this as a polynomial or some such function, where if I look at now the maximum of this, it corresponds to, or it's even equal to, the optimal. The important thing that we should keep in mind is that this function should be easy to evaluate. If I give you a point x, then you should be able to tell me what the value of this function at this point x is. But it doesn't have to be convex. It could be non-convex. And in fact, our examples will be non-convex. And once you have such a thing, the algorithm is really very simple. Okay? Just sample a point at random and round it. And often the rounding is also quite simple. I'll give you one example. So no solving some complicated convex program, no real stability, no nothing. It's all just kind of straightforward stuff. And to prove that this works, we have to ensure that this function f that we use as a proxy for the optimal has a certain smoothness property, which we defined earlier. So let's look at an example, and let's look at a sketch of the proof of the second theorem. And remember that this theorem was about partition matroids, and let's just look at a simple setting where there are m parts and each part has two vectors, and from every part you are supposed to pick exactly one vector. So I give you vectors v1, w1, v2, w2, vm, wm, and I ask you to pick one vector from each of these pairs, vi, wi, so that the determinant of this u1 to um is maximized. It turns out that we can look at the following non-convex function, which actually captures the problem exactly. So think of t as a number between 0 and 1, a positive number between 0 and 1, and define a vector function uit, which is just the convex combination of vi and wi at the point t. So you take t times vi plus 1 minus t times wi. And at a point x1 to xm, so these are now numbers between 0 and 1. You compute the vector ui corresponding to what the value here is, and look at the determinant of these vectors. So this is the function. Okay, it looks like a nasty function. What you can prove is that the optimum of this problem is equal to exactly well, this is obvious, right? So then if I let x to be only 0 or 1 valued, then so in each case you're either selecting vi or wi. So that's exactly the same problem as before. So there is nothing non-trivial here. Well, this is also not non-trivial. This just follows from the fact that these functions have some underlying multilinearity, and that's very important here. It's a non-convex function, but it has some underlying multilinearity, which you can use to show that if I now relax this 0, 1, m to the hypercube, where you consider even interior points, then the value doesn't change. So it's a high degree non-convex, but kind of a multilinear function. A multi-affine, rather. Okay, so this is the polynomial. I just told you the relaxation, and the rounding. I guess there are many experts here who would just probably need a couple of minutes to figure it out, but the rounding just follows from looking at univariate restrictions of this polynomial and observing that because of multilinearity, one or the two endpoints of the interval would maximize, so we can just do it in polynomial time. So there's nothing magical about it. So the thing that we need to prove is that this function has this smoothness property. Yeah?
Is its log, is the log of determinant concave or something, or not? Maximizing
No.
that is the same as maximizing its log, so?
It's not, I mean, no. Yeah.
That is concave, but not in this.
Yeah. Not in this parameterization, no. So I have to show you that the function f is smooth, okay? And what that means is the following. Now suppose I look at some univariate restriction of this function and I get a univariate function g of t. Well, it will be of this form, absolute value of at plus b, where a and b are some constants. And let's look at an example where a is equal to 1 and b is equal to minus 1 by 3. Then proving smoothness is essentially the same as, or is exactly the same as showing that the measure of those t's where the value of gt is less than c times the maximum value is at most 2c. And the proof just follows from picture. So this function, absolute value of at plus b, looks like a v, okay? And with a root, as you can check, at 1 by 3. So this function vanishes at 1 by 3 and it's linear. And this is its maximum value, which happens here. And this is the line corresponding to c times the maximum value. And now you can just, I mean, it's just a simple high school calculation to look at what is the measure of this set where the value is less than c times g max. And that turns out to be, in this case, 2 times, because there are two sides, times 2/3 of c, where this 2/3 you get because of the setting of a and b. And no matter what a and b was, this number can be at most 1, and so the total mass that you get here is at most 2c. Okay. So that's again this uses multilinearity. Yeah.
Is your rounding a step of the randomization of a simpler randomized algorithm, or is
No.
Get is log somewhat, right?
But in what, right? So this is a strange kind of a thing, right? So yeah, so I mean there are ways to encode the problem as a determinant, but then we don't necessarily then we lose all these nice properties like multilinearity and smoothness and so on. Yeah, perhaps if I had more time, I would have shown you how this thing differs from the Nikolov-Singh result, which also uses determinants and some kind of relaxations based on that. But then you get convex relaxations. But then it's not clear how to round them. Okay, so this is essentially the whole proof, assuming the anti-concentration inequality. I guess I want to say something about the anti-concentration, so I'm going to just tell you what happens in the regular matroid case, what the function is. So the function is actually interesting. It's the following. So remember that in the regular matroid case, what we would need is these vectors, not only these vectors which are given to us, but a representation of this matroid. And so we look at this function, okay? So it's the absolute value of determinant of v x b transpose, where x is a diagonal matrix corresponding to the variables x1 to xm. So notice that this is again a highly non-symmetric function, and a pretty nasty convex and non-convex function. There is no hidden convexity in any of these arguments. Now here you can prove that the optimum is not exactly equal to the maximum, but within some 2 to the r factor, multiplicative 2 to the r factor of the optimum. So in particular, if the optimum is 0, then this is 0. Okay, this relaxation at least captures the 0 versus non-zero property and also gives a reasonable approximation. And then you can follow similar steps. I mean, the rounding is a bit more complicated because you get something more than a tree in this case, and then you have to remove some elements and prove that you don't lose in the approximation. Okay, so let me now, in the last 5 minutes, give you some intuition about the anti-concentration theorem. So even if you're not interested in the applications, I guess this is something which seems quite general and maybe useful in other places. So this is what we would like to prove, that we are given this smooth function, the probability that the function takes value at least c to the minus m times the optimum value is at least 1 over m. So let's say x star is an optimal solution. So x star is a point where f of x star is optimum. And now let's define this following event, ai, where all I have done is fixed the last, from I plus 1 onwards, the value which correspond to the optimal solution. The first I minus 1 are arbitrary values in 0, 1, and the ith on this side is xi, and on here I have replaced it by xi star. Okay? And I would like to understand for what choices of x1 to xi, or what is the measure of those x1 to xi where this holds, that the function does not decrease so much. Okay? And the smoothness property implies, and this is perhaps requires a couple of minutes to check, but the smoothness property gives us that the probability of this event happening is at least a half. And so what we can try to do is try to chain this argument. Okay? So we can look at the intersection of all these events. So if it is true that A1 happens and A2 happens and A3 happens and AM happens, then we know that we can derive such a bound, and hence the probability of this event is at least the probability of this event, because this event implies that. If you have this inequality for all I, then you can just chain them out. At the end, because you have fixed everything, you get opt, and in the beginning you just get f of x. So you get this. So this is sufficient to establish a lower bound on this. I mean, the issue is that they are not independent, but you can try to do the following kind of a conditional argument. You can use Bayes' rule to write this intersection as a product of these probabilities, where you have condition one at a time. And the smoothness can again be seen to imply that the probability of AI happening conditioned on all the previous events is at least half. It's a strong property. Okay? So there are some kind of high-level similarities to real stability, except that we don't really use it anywhere, because it's not true in our case. Okay, so this simple argument implies that because each of these events happen with probability at least half, that you can get the probability that the function takes value at least 4 to the minus m times the opt is at least 2 to the minus m. And now the question is whether we can improve this 2 to the minus m to something like 1 over m. Well, you can play around and you can recover this bound of m to the minus m from this, but if you want a constant probability here, but this argument is not going to work beyond this.
So far you've used only coordinate-wise smoothness.
Yeah, that's sufficient for us, yes. Okay, so let me just show you what the picture. I mean, this part is kind of quite complicated. It's technical. I will not be able to explain the whole thing, but let me just show you a picture. And the key to this proof is defining these random variables yi, which are ratios of the function at xi, where I flip the bit xi from optimal to random. Okay. And so what it does, what we do in our proof is to look at this measure space or look at this space and do a kind of a partitioning of this space, a certain hierarchical partitioning into where each set S has is indexed by m numbers. Each can be up to a log m. So there are 2 to the m such cells, we prove that the property that the way we construct these cells have the property that for every point in this set, we can lower bound the value or the ratio of f of x by optimal, by some number. Okay, and these numbers are carefully calculated. And this, so this is the technical heart of the proof, and this is roughly implied by the fact that you can view the smoothness of f as some kind of tail bounds on minus log of these random variables yi. Okay, I'm done here. Okay, so this is technical. So Chandra is giving me like, okay, enough. So I'll skip through it, and then we require some combinatorial counting argument to do this. Okay, so let me just conclude. So we gave these efficient approximation algorithms for constrained subdeterminant maximization problems. They're computationally easy, don't rely on real stability. We also give a new anti-concentration inequality for simplices. And a natural question is, can we generalize this from simplices to more general convex bodies? Okay, this will be useful in improving the approximation guarantee. And finally, a question that I find very interesting is, can we de-randomize our result? Can we so many of these probability inequalities have this flavor. They say that with high probability, some event holds. And in this case, we have a similar statement that if I pick a random point, then the probability that the value of the function is close to optimal is large. Can we find such a point deterministically? Thank you.
A quick question while Nima is setting up.
You got it? Sure. Good. Yeah.
So it's one on the extremes, but then something else on in between.